Hello, I'm Zhang from the University of Bath, and today I'm going to present our recent work on a game theory reward model for federated learning with probabilistic verification. Let's get into it. As you will be well aware, in recent years, machine learning and in particular deep learning has been growing in popularity. And as it's growing in popularity, those models have only grown in size. And with that increase in size of the models, it means we need more training data and more computational resources to train those models. It's desirable that we would be able to pool our resources and share the load of training between distributed agents so that we can share our resources and train those models faster and more easily. So federated learning provides us with a framework for doing this. It specifies a central model, which is the node responsible for the training. So they are the one that actually wants the trained model in the end, and they will coordinate the agent and aggregate the models. And then we have the agent, which are your distributed elements who will be performing the training on behalf of their central node independently and remotely. So you have a central node which start by broadcasting the model out to each of the agents. The agent and then train the OM models locally on the OM private data. They send the trained models back to the central node. The central node then aggregates the models together and it can then rebroadcast them, and the process can be repeated. The benefit of this is that we can do some cryptographic techniques to ensure that the data and the parameters being shared between models are private. And also each federated agent can have its own personal training data that it doesn't need to share with anyone else. So this is a fairly simple procedure, and a logical next step of this procedure is we might want to offering some rewards for the agent in exchange for the training. This will help incentivize more agents to train the model, and it will therefore speed up the training process. However, you can imagine a marketplace where you can, as a central node, you can pay or put up a price that you will offer for people to do the training on your behalf, and people can volunteer to do it on the system for you. The issue, once we start to introduce reward, is that they are then going to be agents that want to exploit those rewards and earn those rewards without putting in the work phase. Here we call those free riders. So free riders are going to be performing attacks to pretend and look like they have done some training without doing anything. So there are some techniques called proof of training that have come out of cryptography that allow us to verify that the free riders or the agent have actually trained and are not engaged in free rider behavior. But the issue with those techniques is that they are very, very expensive to run. And the whole point of federated learning is that we are trying to reduce the computational load on the central node. So if we have to do all those expensive verifications on our agent, then it's sort of defeating the point of doing this in this federated, distributed manner. So what we need to do is come up with some way of reducing this verification cost. We suggested that we use a probabilistic-based scheme. So we verify agent with a central probability. So there's a chance they will get verified, and then we will randomly verify them according to that chance. We can think of this as a game, as a game theoretical framework where agents are trying to maximize the reward and minimize the training cost. And the central node is trying to minimize the amount of reward it pays out, as well as minimize the probability it needs to run the proof of training. But it still needs to disincentivize free riders from participating. So our goal here is to set up a scheme where an agent expects to earn more by behaving honestly as it does by behaving as a free rider, which means that any logical agent is going to decide to act as an honest agent rather than as a free rider. So we can begin to formulate this more properly. We are going to see we have m distributed nodes. Each node has its own dataset, and we see that the size of the dataset is ni. The total amount of data shared between all our agents is big N, which is just the sum of all the data. Individual dataset, we then consider each round of training to be a game. So we can denote that with a time step t, and we are also going to assume that our proof of training routine is completely accurate. So when we run that proof of training, we know for sure whether that agent is an honest agent or a free rider. So the central node, like I said, they are in the only agent really we have control over here. And they are going to set the reward and the verification schemes. This gives us the parameter r of t, which is the total reward giving out at round t. This is going to be have to be greater than 0. And we also have our probability function p, which is the probability of subjecting agent I to proof of training verification at time t. And you can see this probability function takes in the amount of data that agent is training as a parameter. And we will get to that, but the general idea is that we are probably going to be rewarding agent based on how much data they train on, because that's proportional to the amount of work they put on. So the probability of them being verified is also going to be proportional to the amount of data they are training on. So now let's write the cost function. Our cost function is written as the total reward that the central line has to pay out, plus the cost spent validating. So this validating cost is based on our constant V, which represents the cost per unit data to validate an agent. And this is multiplied by the sum over all of our agent, of how much data that agent has times by the probability of verifying that agent. So this is our expected validation cost. Is this whole term on the right-hand side here? We take this cost function and turn it into a utility function. But we all need to do is to include now an extra term, which is the function g. So g here is going to represent the fact that the central node wants to train the model. Training the model is going to provide it with utility. And we can see that this utility is probably in terms of the amount of data that the model has been trained on. The more data we train it on, the more data, the better our model is going to be. And so this is going to provide utility to the central node. We can see that utility to the central node is a function g minus its cost that we just described above. Very straightforward. So we then have to consider honest agent. So those are going to train the models as we set out in the federated learning routine. We are assuming that the cost of training is going to be proportional to the amount of data they are training on, which is ni. So we allocate the reward proportionally to the fraction of the data they are training on relative to all the other agents, which we can see in the middle here. We can then define an honest agent's utility as this term, the reward they will receive, minus the cost of training, which is alpha, our training cost parameter, times by the amount of data they are training on. And then we also have to factor in the transmission cost, which is how much it costs them to send data to the trained model to the central node. This could also be framed as effectively interest fee, like or deposit, like the agent have to pay, but we consider it as a transmission cost here. So free riders are not going to perform any training, and the only cost is going to be transmitting the parameters. We are assuming that whatever they are doing in the attack is negligible in cost, so they have a chance of being detected. So we need to reduce the expected reward by that probability. We take 1 minus the probability of being detected and multiply the expected reward by that, and then we are going to still pay that beta, which is our transmission fee. But there's no training fee here. So we are going to be able to try and find out our values R and P for our award and verification schemes. So our goal is to minimize the cost of the central node while still keeping the agent acting honestly rather than as a free rider. So we fix the total amount of training data big N. We assume that it is to be constant without loss of generality. And we are also going to drop the T from the notation because we are going to consider each individual round training to this to be its own. We are not going to worry about a history of behavior. We are just going to assume each agent is equal each round and treat them as such. So at the top here, we can say that we are just minimizing the cost function here with respect to our reward and probability schemes. This is just the cost of the central node in equation 1 there, and we are just subject to two constraints. Constraint number 1, there is our incentive probability constraint, which is saying that the expected utility gained by acting honestly should be greater than the expected utility by acting as a whole free rider. So we are saying that we need to make sure that our agent should want to behave honestly. The most reward has to be earned by behaving honestly, and then we additionally have our individual rationality constraint, which is equation 3 here, which just says that our reward should be positive. Our utility should be positive. I should also say that our reward minus cost. Otherwise, nobody honest agent or otherwise would want to participate. So we take that and we are able to produce our theorem 1. The proof for that is in the paper, but the result are that we can characterize our reward scheme and our probability scheme. So you will see both of those have this maximization function here, which I will talk about in a second. But the reward function is this maximization multiplied by the total amount of data being trained on. And the probability of A being verified is alpha divided by this maximization function, alpha there being our cost per unit data for training. So this maximization function is not really an intuitive explanation for it. It's more of just a mathematical result we got. But you can see the left-hand side here will correspond to our constraint number 1, our equation number 2, which has constraint that said the reward for acting honestly should be greater than the utility for acting as a free rider, and that the square root of their validation costs times where the training cost. The right-hand side here we have corresponds to making sure that the expected utility is 0. So together, this equation is essentially enforcing our constraint. And again, our reward is made by multiplying this by the total amount of data. And the probability is by dividing alpha by this value. And so you notice that this function is essentially in terms of per unit of data, because we have to multiply by the amount of data, or we use alpha, which is also per unit of data. So anyway, this is going to be this theorem, and is going to tell us what our optimal values of alpha and p are. And our second result here is that we can actually characterize the optimal amount of training data to train on. So this is because we are assuming that our utility for the neural network or our model is concave, as it will be. We expect that there will be diminishing returns as we increase the amount of data. If we double or triple the amount of data, we are probably going to slowly get less. Um, and we can write this as 2 times the square root of our validation cost times our training cost, divided by the differential of our function g. So it does require you to know what g is, but as long as you do, we can actually calculate that the optimal amount of training data is, which I think quite a neat result. So this takes us on to the experiments. Our experiments have 3 main objectives. Firstly, we want to confirm that our verification probability function actually minimizes the cost of the central node. We also want to evaluate how quickly the model converge when we are using the verification and the probability reward schemes. And finally, we want to assess the effect of using different data sets just to make sure that our results are valid on all data sets, on all kinds of different data sets. So we use 3 data sets, Minister Fashion, Minister, and Seften. So those are fairly standard. They all consist of small images that need to be characterized categorically. So we use a small, fairly standard CNN convolutional neural network that we train on those data sets, and we repeat that 10 times from scratch or reset all the parameters. Run 10 new experiments on each of those data sets. Excuse me. The data is allocated randomly between the agents, and additionally, the central node has its own training. So after it's aggregated the model, the central node will train the aggregated model just to tune it a little bit. So the central node will announce the reward and the verification scheme, as we described in 0. Then each agent will decide whether or not it wants to join in. So the agent will try and estimate the expected reward they are going to get by participating. And this will be different whether they are an honest agent or a free rider. We then measure the actual cost of the central node after every round, so that we can measure our return and our cost. So here we can see a plot. On the x-axis, we have our training epoch, and one epoch corresponds to 1 round in the federated learning. On the y-axis, we have the accuracy of the training model. And we can see here is the red of the line, the lower probability of running our verification, and the blue of the line, the higher the probability. And what we can see here is that when the probability is greater than or equal to 10%, the accuracy is fairly high and almost identical between rounds. And when the probability is between 0 and 10%, then the free riders are joining, and that they are positioning our training and significantly reducing the effectiveness of our training, and therefore decrease the accuracy of our model. So this is essentially demonstrating that free riders are not good, and it also demonstrating that this cutoff point, not 1, which we actually predicted from the theorem, is the point where free riders will start deciding to act join in. And the second graph here shows the probability of running the verification along the x-axis. And then we have loss in blue on the x-axis, on the y-axis, and cost in red on the y-axis. So loss represents how much error is involved in the neural network. We want to minimize loss, and the cost is the central node. So we also want to minimize that. And what we want to see here is the dotted line at 10%. This is a probability that our theorem predicted should be the optimal, and we want to see if the probability of verification is lower than that. Then the free riders are acting and getting involved. So on the left-hand side of the line here, as we go to the right-hand, as we see, the loss remains basically stable because the free riders are no longer getting involved. But so the loss function isn't actually changing that much, but the cost does increase because the higher our verification probability, the more we are spending on verification. So we can see that the point we predicted, which is p, equals 10%, which is the optimal that minimizing loss and minimizing the cost. So this is a confirmation of our theoretical result. So that brings us to the conclusion. We introduced a novel game theoretical framework for analyzing federated learning. We described the utilities of the agent and the central nodes and characterized those by the reward and the probability verification schemes. We then found the scheme that maximized the utility of the central node while disincentivizing free riders from participating. And then we went on to confirm those theoretical results with our experimental result. That's it. Thank you for listening, and I hope you found it interesting.